If we want to build anything on the moon, it makes sense to build it using a fleet of construction rovers. Fortunately, the moon is mostly made out of stuff we can use to build rovers and machines. But no matter what the human to robot ratio is, we will always have a human-centric economy. And unfortunately, there is nothing human-centric about the moon. No organic compounds, none of our favorite breathable inert gases, no edible carbohydrates and hydrocarbons like maltose and microplastics, and realistically, no meaningful amounts of water for anything larger than a few dozen people. And this is where our logistics problem arose, derived from lunar landing frequency, which greatly crippled our lunar economy's growth potential, addressed in the first half of this series. And we solved this problem, which was mostly caused by the need for orbital refueling of super heavy lift rockets, by constructing an orbital port, which is used to transfer payloads from a rocket to a steel skeleton cargo freighter, which takes that load back to the moon. Now, you'd think it would be as easy as just landing on the moon, unloading, then launching back and repeating the process. But here, our real troubles begin, for in those details, there be devils. You don't want to land the freighter too close to the base for safety reasons, but you do want to unload your cargo close to the base for efficiency reasons. You also need to figure out a way to refuel the vehicle, which means you need a fuel depot, but you don't want that fuel depot to be anywhere near your landing spot for explosive reasons. And also you'll want to load your freighter with empty containers to return them to the port for that closed loop container trade. So what, do you land away from the base and use a bunch of gantry cranes for everything? Do you load its cargo onto a rail cart? Do you add wheels to the freighter, adding to its weight? Do you grab it with chopsticks? Well, what if you land the freighter on a landing pad far removed from the base, and that landing pad itself can move the freighter towards the loading, unloading, and refueling area near the base entrance, sort of like the NASA crawler used to move rockets into place? And what if we gave that freighter a little boost in its liftoff by accelerating the landing pad to a few dozen kilometers per hour by simply making the rails longer? But why stop at a few kilometers per hour? Why not go up to a few kilometers per second and use the landing pad itself to also launch space freighters from the lunar surface back into orbit, so the freighters themselves wouldn't need to carry the dead weight of lunar launch hardware and fuel? We could accelerate to orbital escape velocity using electricity, so the landing pad is like a reusable catapult. If we space two rails apart for each leg and run an electric current through the rails, and then the landing pad legs ride upon a conductive armature which connects the circuit, a railgun. Lunar escape velocity is 2.3 kilometers a second, so if we maintain a gradual acceleration of just 1 g, that of regular Earth gravity, then our track length would need to be about 300 kilometers, and it would take 4 minutes to reach escape velocity. At an acceleration of 2 g's, our rail length is halved to just 150 kilometers and 2 minutes, and at 3 g's it would be just 100 kilometers or 62 miles for only 81 seconds. While 3 g's is perfectly fine for cargo, we may want to use this same system to launch people, and 3 g's can be a lot on the human body, but it can be withstood for short amounts of time. For reference, astronauts on rockets experience it for up to a minute, while fighter pilots experience 6 and even up to 9 g's for a few seconds. However, considering tourism would likely be a major part of our lunar economy, it makes sense not to limit our visitors to only highly trained fighter pilots. Legally, roller coasters can pull 3 g's for no more than 12 seconds, so a passenger version would likely need to be about 300 kilometers, although we could shorten this by having a gradual increase in acceleration and accelerating more towards the end, pulling 3 or even 4 g's in the last few seconds. But initially it makes sense to just use this for cargo per the cargo freighter, and secured cargo can easily accelerate at 4 to 5 g's or more without much of an issue. 5 g's would give us a track length of just 25 kilometers or 15 miles, and would achieve escape velocity in just 48 seconds. But even this is a significant distance. It would be by far the largest thing ever built off-world. However, it can be made of very rudimentary components, just simple aluminum rails created from in-situ resources using a robotic construction rover fleet, either automated or teleoperated from Earth. And it would be worth the investment because by saving the freighter from also having to accelerate itself up to escape velocity, we save a lot more capacity for cargo, which means more resources for people, for more habitats, for more freighters, for orbital port expansion, for more cargo, for more resources. And so what we have just arrived at, through a bottoms-up, step-by-step problem-solving approach, is the creation of a reusable, electric-powered system used to drive mass into orbit, a market-driven mass driver. But it has issues. The concept of the railgun is over 100 years old, first conceived of in France during World War I, and everyone from the Nazis to the Chinese, the Russians, Indians, and both the US Army and Navy have all poured significant resources into the effort at one time or another, with the Japanese most recently picking up the mantle. Despite all this, no railgun has ever been fired in anger. No designs mass-produced. It has never been used in war for the same reason it's considered a bad lunar mass driver design: ablation. Essentially, rail wear, gouging and grooving due to the high stresses imparted into the rails from heat and arcing and forces involved in accelerating a projectile up to 2 to 3 kilometers a second within just a few meters. Here's a short, approachable paper summarizing the current state of railgun tech research. Designs and failure points I'll link in the description, but the main takeaway for us is the technology works, but ablation is the major bottleneck, limiting the system's reusability. The US Navy was able to get off about 400 rounds before a barrel needed to be replaced, and was approaching 1,000 rounds before the program was shut down in 2021, but the major costs involved make it impractical as a weapon. But we aren't trying to build a weapon, we are trying to build infrastructure. All previous research has been done in the context of trying to make Navy guns with super short track lengths and super high acceleration rates, like tens of thousands of Gs of acceleration. Very demanding, lots of ablation. And it's shocking they even got up to 400 rounds with that. But we aren't trying to fit our railgun into a battleship. We can make our track length very long, and we can make our acceleration rates pretty low. But even with long tracks and low acceleration rates, we'll still have ablation. And this is why railgun designs have largely been considered bad candidates for lunar mass drivers in favor of coil guns, which suspend their payload between copper coils, allowing for no surface contact and no structure wear. But the issue with this approach is the payload size would be constrained to the diameter of the coil gun mass driver, which means it won't work well with our freighter design. A design which was logical in being a basic, easy to construct platform, meant to simply move cargo back and forth. The only reason we reached mass driver was as a means to amplify the effectiveness of these freighters, which themselves were the solution to our original market-driven supply problem. On the moon and in space in general, construction costs are the largest costs, which is why we need to put premiums on simplicity, like with the freighter design. And the coil gun mass driver would have much higher construction costs derived from a more complex architecture demanding more resource intensity per cubic meter compared to that of the rail gun, which is basically just simple suspended rails and capacitors. Now sure, with the coil gun, you have rapid reusability, no repair needed, and so while your payloads have to be smaller, you can launch a ton of them in quick succession. But what I think most people miss, probably because the design we're using derives from a coil gun, but it isn't a gun. We're not launching bullets, we're launching spacecraft. You cannot just shoot chunks of the moon out of this thing to a predetermined destination. The loads still need to be powered. There's all kinds of perturbing forces acting on any object at any given time. Consider the sun and moon and earth all interact, which is why some Lagrange points are unstable. Even the varying topology of the nearest planet, different density at say mountain ranges versus plains, has an effect when an object is within the Hill radius of that body. So any payload will need to perform station keeping and descent burns to get into a specific altitude or orbital plane. So we are talking about launching spacecraft which have to be manufactured and fueled. And so the mass driver really needs to be thought of as a first stage for a rocket more than anything else. And the same principles for why big rockets are better still applies. Scale. So with this context in mind, the question of railgun versus coil gun becomes, do you want to launch 10,000 tons aboard 2 large spacecraft, or 10,000 tons aboard 1,000 little spacecraft? In either case, it makes sense to build those spacecraft on the moon, and it's much easier to build 2 large spacecraft than 1,000 little ones. As if that wasn't damning enough, the 1,000 spacecraft, basically little rocket pods, have to be recaptured and transported back in a closed loop cycle. Are you just throwing them away? This means they need to be decelerated back to the lunar surface somehow. Under their own power would be very inefficient, but maybe we could use some sort of big platform to capture all of them in orbit and then transport them back to the moon and decelerate them down to the lunar surface. Oh wait, that'd just be the freighter, but instead of transporting cargo in its containers, it would have to transport these little spacecraft, which are too small to be used to import a Starship-sized load unless you want to redesign the entire orbital port to be a much more complex sorting facility to piece apart every incoming payload into 100 different bundles to fit into these pods, which is just stupid. A potential solution could be to make these little spacecraft much bigger, so a single one can launch several Starship payloads worth, and maybe you could land it on a landing pad that moves, and maybe you can move that landing pad really fast on some electrified rails to help with the first stage. And so you can see how a railgun design is optimal. But we still haven't solved that ablation issue. But I'm going to propose a radical solution to that. What if, and hear me out, what if we simply embrace the ablation? What if we simply embrace the fact our rails will be damaged and just repair them between launches? Lunar regolith contains lots of iron, chromium, and aluminum, and a lot of science fiction books and shows such as Artemis focus on the aluminum aspect, showing lunar bases made out of giant aluminum domes, which I always found funny since to get aluminum, you have to run regolith through an electrolysis cell. But running regolith through an electrolysis cell will yield lots of products, not just aluminum. Really, it just removes the oxygen gas and separates the metallic components into stratified layers of molten metals, including aluminum, but also chromium iron or ferrochrome, typically being more abundant, and molten ferrochrome is a hop and a skip away from steel. Just add carbon. Even if you don't add carbon for steel, ferrochrome itself is a strong metal, like raw iron, much stronger than aluminum with a higher melting point, which is the more important metric when on the moon given the drastically fluctuating day-night thermal temperatures. This is why I always talk about building nearly everything out of steel, the shelters and ships and rovers. Why bother with aluminum, the balsa wood of metals, when you have the option of using steel? But for the mass driver rails, aluminum actually makes the most sense because aluminum has higher electrical conductivity than iron. And even though we are embracing the ablation, like alcoholism, we don't want to embrace it too much. The lower the resistance, the less ablation occurs, and while copper has the lowest resistance, it's pretty scarce on the moon, so we go with aluminum. And over time, we can reduce this wear by upgrading the rails with cooling systems and composite platings. By cooling down the rails to 50 Kelvin or negative 220 degrees Celsius or negative 370 degrees Fahrenheit, we could reduce resistance by an order of magnitude. And this sounds like a lot, but remember, the lunar night already drops down to negative 133 degrees Celsius or negative 208 degrees Fahrenheit naturally. But in the near term, just brute forcing it works, because on the moon, resources are ample and power is abundant. So with all of this in mind, one could easily conceive of a lunar construction rover built around an electrolysis reactor that can print rails. Regolith goes in one side, rails come out the other. And a slightly different, modified version of this rover could simply run along the rails between launches, repairing damaged areas. But okay, this is an oversimplification. Really, you need a construction rover fleet because the rails themselves should be on a surface that isn't just plopped down onto the moon because the electrostatic dust will interfere with launches. Fortunately, you can lightly melt regolith into what is essentially a rough asphalt paste using orbital mirrors to concentrate sunlight, or by creating the evil moon version of a Zamboni, a nuclear-powered melting rover. It doesn't matter, whatever is easier. Also, the lunar terrain isn't nice and even, it's rugged and boulder strewn, so you also need basically a lunar bulldozer to clear the path. You know, basic construction stuff. I've been asked on a few occasions what a good business venture for the moon would be today, and my go-to answer is something like this: the creation of a construction rover fleet, which wouldn't just be for mass drivers, but could be used to make basic roads and launch pads and structures early on. NASA is interested in dust mitigation techniques, and melting all the dust in your area into a hard paste is an effective, if somewhat inelegant, solution. So there's a lot of near-term uses for these sorts of rovers leading up to the mass driver. A good place to start developing construction rovers is to start developing hydraulic systems that will work in the vacuum of space, specifically the lunar environment. During Apollo, NASA avoided developing and using fluid hydraulics because they feared the regolith would interfere with their function too much and didn't want that to be a potential failure point, and since they weren't reusing their vehicles, they could afford to ignore that and just go with single-use designs such as crush canister suspension on the LEM. But any lunar development efforts will need reusable vehicles, like, obviously. So yeah, space hydraulics. It's not as flashy as reusable rockets, but it's effective. And if you have the right connections and CV, you could probably get NASA or DARPA funding for it, and once developed, start a lunar construction rover robotics company. Anyway, this video is for education and entertainment purposes only, so don't sue me when you go bankrupt. But also maybe throw me a bone when you become a trillionaire? Alright, in the next video, we'll talk about what building this mass driver will do for us, how it will really open up the heavens and pave the way for solar system-wide growth and expansion. So like and subscribe to tune your algorithm. Thank you to Logan Mars, Romeo Weinrich, Leo, Ted Thayer, Adam Rudanis, Rick, Jonathan Crone, Mustafa Mond, Joshua Paletti, and Stephen Reed for supporting the channel.